monoxide requires 1 mole of ammonium nitrate. So you end up with 5.67 mole of ammonium nitrate. You do the same thing for water, because this is one reactant producing 2 products there. So the number of moles of water that can be produced is the moles of ammonium nitrate multiplied by the conversion factor in this case. Every mole of ammonium nitrate will produce 2 moles of water. That's given in this balanced chemical reaction equation. So you will end up with 11.3 mole of water. So that's the third step. The fourth step, we're going to ask you to convert these into grams. Formula is given, periodic table is given, so we do the calculation. Each mole of dinitrogen monoxide is equivalent to 44 grams. You get this information from adding the mass of atomic mass of 2 nitrogen atoms and 1 oxygen atom. Okay? And each mole water, that 2 was missing, H2O. So that's the reason why you see marks on the screen, because sometimes when people get carried over and when they see mistakes on the slides there, and they try to write it on the screen there. Okay? I've done that a couple times already. It's supposed to be H2O here. So 11 moles of water converted into grams, and 5.67 mole of dinitrogen monoxide converted into grams. Now, if you add these 2 numbers together, you get 454 grams. So mass is actually conserved. If you look at this, in all the information given here, you start with 454 grams of a compound. The reaction is finished. You produce 2 compounds. The total mass remains 454 grams. Mole, 5.67 mole of one compound, and it was 5.67 mole of one, 11.3 mole of the other. Okay, so do not assume the moles are going to be conserved. No, only the mass. So the mass is conserved before and after the reaction. And this is the perfect example to show the law of conservation of matter. You start with a certain amount of matter, you end up with the same amount of matter in different combinations, different compounds. Okay? Originally, nitrogens and hydrogens and oxygens are all tangled together. After the reaction, they recombine. You end up with nitrogen and oxygen tangled together, water and hydrogen and oxygen tangled together. Okay? So, but the total mass is still 454 grams. So that's something that we want you to remember. When you do a chemical reaction, the mass is always conserved. Therefore, the chemical reaction equation must be balanced. You have to have the balanced chemical reaction equation. Okay, so when you do stoichiometry questions there, in order to solve stoichiometry questions there, you must go through moles using molar mass and molar ratio as conversion factor. So you cannot do this calculation without writing the balanced chemical reaction equation first. So this is always going to be the first step. You need to know the formula of each of the chemicals involved. You need to balance that chemical reaction equation. Going from reactant in grams, you need to convert it into moles. The molar ratio as a conversion, molar mass as a conversion factor. Where did you get the molar mass? Well, periodic table. You're adding the atomic masses together, all the atoms involved in the formula. So from this step to this step, gram to mole of the reactant, molar mass is the conversion factor. And then from moles of reactant to moles of product, molar ratio in the balanced chemical reaction equation. That's your conversion factor. And going from moles of product to moles in grams, molar mass, again, is your conversion factor. So, dimensional analysis. All you need to do is to be able to identify the correct CX, conversion factor. The conversion factor lies in different places. In the list of equivalent quantities, in the periodic table, in the balanced chemical reaction equation. There is nothing new. Once you understand how to do dimensional analysis, you discovered the secret of chemistry. It's very easy, very simple. You just have to be able to identify the conversion factor. That's all we want you to be able to do in this course, please. Okay? So, the strategy map there, going from gram to gram of reactant to gram of product there. And again, multiple steps there. The first step is always write out the balanced chemical reaction equation. conversion factor is identified, and you do the calculation. Okay, so another practice problem there. Chemists try, so we got to try this. Okay, so in one day, if you take 105 grams of glucose, well, that's roughly about 3 sodas that you take. Any soda, not just Coca-Cola, Pepsi, or Mountain Dew. You should get into the habit of reading the labels on anything that you're going to put into your mouth. Because in Chinese we have a saying, all diseases come in from your mouth. Initially it was that, well, maybe you eat something not clean, you end up with diarrhea. Now, everything, obesity, diabetes, high blood pressure, everything comes in, comes into your body. Every disease comes in from your mouth. Okay? So you have to get into the habit of reading the labels. What's in there? When you're taking 3 soda, 12-ounce can, you're taking in 105 grams of sugar. That's a lot of sugar. Do you really need that much sugar? Probably not. But why are you taking that much sugar? It's always a side note there when I teach chemistry there. I always want to relate things to your daily activity. You measured 1 gram of solid yesterday in the balance room. You know 1 gram, that's a fairly large pile. Multiply that by 100. That's how much sugar you put into your body when you drink 3 soda. Of course, you can say diet, there's no sugar in there. Yet, there's nitric acid, there's phosphoric acid in there, citric acid in there, and carbon dioxide compressed in there. A lot of those chemicals, you may not need them, but you argue, they taste good. I want to enjoy life. Well, yeah, enjoy life, but pay attention to what you take in there. Too much sugar, you're going to generate a lot of problems. And matter of fact, just last week, I think, there was an article published in the Journal of American Medical Association, published an article there. And the most detrimental thing that you can put in your body is sugar, too much sugar. Okay? So that's something that you want to pay attention to. Now, if you consume 3 cans of soda, and there's 105 grams of sugar, glucose, how much water are you going to be producing? How much, assuming there's enough oxygen? You breathe in the oxygen. Okay. So we ask you, how many grams of water are produced by the reaction? Now this is purely theoretical. We're not saying, well, all of that 105 grams of sugar, we assume all of the sugar completely react with oxygen. So the reaction is 100% complete. In the end, all of the glucose are being converted, and there's enough supply of oxygen, and all of the sugar is being converted into water and carbon dioxide. So, stock count question there. Grams of glucose, grams of sugar, to grams of water. That's the calculation. We can't go from grams of glucose to grams of water directly. We have to convert grams of glucose to moles. Each mole of glucose will give you 6 moles of water. And whatever number of moles of water is being produced based on that mole ratio, convert it back into grams. So that's the calculation that we need you to be able to do. And so 105 grams of glucose sugar, each mole is equivalent to 180 grams. Okay, that information sometimes is given, sometimes no. As long as we give you a formula, as long as we give you a copy of the periodic table, you need to be able to figure out that information. So this is the number of moles of glucose that you take in, equivalent to 105 grams.